So what we want to do is we're going to write down the energies for a rock falling down. So you can't get too much simpler than that. We'll say the rock has a mass of 1 kilogram, and it starts at rest up here in the air, and then it eventually makes its way down to the ground. Well, actually probably pretty quickly, thanks to gravity. The ground, not the round. Okay, so we're going to have a y-axis. And we'll have a few points that we pick out here. There's nothing special about these points, it's just to look at it, a few points. So let's say that we start out at a height of 20 meters, nice and high, and then at some time later, the rock is down here at 10 meters. Let's do the rock also at 15 meters. Okay, and we could do it at 5, but that's fine. And then we'll have 0 meters when the rock is sitting on the ground. Okay, so that's 4 places. And for each of those, let's write down the potential energy. We'll just list it for each one. Okay, so up here when it's up in the air, the potential energy is equal to m times g times the height. So m is 1 kilogram. G is, let's just keep these numbers simple. So we'll say g is 10 meters per second squared. We'll round it just a little bit so that we can do these numbers in our head. So g is 10, and our height here is 20. Okay, so 1 times 10 times 20 is 200 joules. So that's the potential energy here. At the next spot, our potential energy is equal to 1 times 10 times 15. I'm just leaving off the units to keep it a little bit cleaner. So 1 times 10 times 15 is 150 joules. And then we would have, at 10 meters, we'd have 100 joules. And then at 0 meters, we'd have 0 joules. Okay, so the pattern, of course, is that we have a decreasing potential energy. What about the total mechanical energy? You might think that we have to first calculate the kinetic energy, but not if we start at the top. Because if we start at the top, the kinetic energy is 0, because it's not moving, it's at rest, plus the potential energy is 200, so the total mechanical energy at the top is 200 joules. Okay, now what about the other points? Well, actually we don't have anything else to calculate. Since the total mechanical energy of this system is conserved, at all of these other points, the total mechanical energy has to still be 200 joules. Okay, now how did I know the mechanical energy is conserved? Well, I have to check for 2 things. The first thing is, are there any external forces doing work on the system? And the answer is no. You might worry about gravity, but gravity is part of the system. The rock and the earth is my system. So no, there's no external forces. Really what that means is I'm pretending there's no air resistance. There's nothing, since there's no air resistance, there's no non-conservative forces working on this. And so, yeah, the mechanical energy is conserved. So then let's write down the kinetic energy. We could calculate this using 1/2 mv squared, and we could figure out the velocity by using kinematics, but that's a lot of extra work that we don't actually need to do. The quick way to calculate the kinetic energy is to take the total mechanical energy and subtract the potential energy. So 200 minus 200 is 0 joules. After all, the rock isn't moving at first. But likewise, we can continue that. So 200 minus 150 joules for the next, and that would be 50 joules of kinetic energy. 200 minus 100 is 100 joules of kinetic energy, and then when it lands, there's no potential energy. Just before it hits the ground, it's all kinetic energy. Okay, we're not taking into account the fact that the rock then stops when it hits the ground. This is the kinetic energy just before it reaches the ground. So in fact, using conservation of mechanical energy is another way to calculate the speed of a falling object. In some ways it's a little bit more straightforward, maybe conceptually more straightforward. Mathematically, just the same as using kinematics. So let's say we want to use this to calculate the velocity that we land with, the speed that we land with, so v at the bottom, just before hitting the ground. The way we could do that is say that this kinetic energy, 1/2 mv squared, has to be equal to the total energy. Well, the kinetic energy plus 0 has to be equal to the total energy, so it has to be 200 joules. And so then v squared would have to be 2 times 200 divided by 1, because we have 1 kilogram. And then So that's 400, and the square root of 400 is 20. Let's try another more complicated example, but following the same kind of reasoning. Although we were not going to write